I'm really enjoying my staying in Cambridge. I love this place, so thank you. So what I want to discuss is the Signorini problem. I think that some of you have seen an overview or a preview of this problem back in January. So let me start with the classical obstacle problem that goes back to the mid-60s and through the work of Guido Stampacchia, Hans Levy, and Jacques Louis-Lyons. So after their first developments, there's been 5 decades of beautiful and deep developments. One of the most important achievements in this subject was the development due to Luis Caffarelli of the theory of free boundaries between the late 70s, 1977 is his fundamental acta mathematica paper, and the mid-80s. So how it, nonetheless, besides the fact that the classical obstacle problem has been so much studied, it nonetheless offers new challenges still present. Yesterday we heard a talk by Andreas about fully nonlinear equations. So there is lots of activity still about this problem. And what I want to discuss is the lower dimensional obstacle problem. So this is also called the thin obstacle problem or Signorini problem. So there has been some very interesting progress over the last decade, starting essentially with the breakthrough paper in 2004 of Athanasopoulos and Caffarelli on the optimal regularity of the free boundary. So the results that I will be discussing are mainly contained in this paper with Donatella, Arshak, Petrosian, and Tumto. The paper is available in archive, so you're free to grab it if you wish to do so. And there is also a part of this paper that is based on previous analysis for singular free boundary points in the elliptic case, and there was joint work with Arshak, Petrosian. So let me start with the classical obstacle problem. You guys have had lunch, I hope. I didn't. So let's start with the meatloaf. So suppose we have a meatloaf and you want to put a cellophane wrapper on this meatloaf. So then you can think of the meatloaf, the configuration of the meatloaf is the obstacle. And the cellophane wrapper, after it adjusts, I mean, if you neglect external forces, if you let it adjust to the geometry of the meatloaf, represents a solution to the classical obstacle problem. Okay, so the mathematical formulation is that we are given, suppose for instance, a C2 function phi, which is going to be the obstacle defined in an open set D. Then we have boundary values psi in W12. That condition there has to be interpreted in the sense of W12, of course. It's on a set of measure 0. So then we have a source term, function f in L infinity, and we want to minimize the energy given there over that closed convex set. So by standard methods in the calculus of variation, there is a unique solution to this minimization problem. The solution is called the solution to the classical obstacle problem. That's a picture that I borrowed so many pictures from the book of Arshak, Henrik, and Nina. So that's a picture for the classical obstacle problem. So if we look at the solution, then we see that the solution satisfies the PDE Laplacian U equal to F in the set where U is above the obstacle, whereas on the set, on the coincidence set, this condition is satisfied almost everywhere. And the first fundamental question, of course, is how smooth is the solution, and we know that the optimal regularity of the solution is C11. So boundedness of the second derivatives is the best that we can hope for. Continuity of the second derivatives is forbidden. Okay, so they are discontinuous in general across the free boundary. The free boundary is the topological boundary of the coincidence set. So the region where U touches the obstacle. All right, so the second fundamental question is how smooth is the free boundary? So the answer to this question is constrained to first finding an answer to the optimal regularity. However, in 1977, Kinderlehrer and Nieringer proved that if the free boundary is a priori known to be, what did I do?
You lost signal somehow. Let me call the computer guy. Computer guy. Maybe not your problem, but the computer problem.
Oh, it's back. It's back. Which one? Sorry.
Not stable free boundary.
Yeah. Okay. So let's see. I hope that. Kinderlehrer and Nirenberg showed that this fundamental result, that if you know a priori that the free boundary is a C1 hypersurface, then it's real analytic. So the free boundary smooths out. And then Caffarelli, in the same year, developed his theory of regularity of the free boundary, and in a series of papers he shows how to go from almost nothing to Lipschitz. He actually went first from Lipschitz to C1 alpha, and then he proved that almost nothing implies Lipschitz. I will not be precise what this almost nothing mean, but it's a condition that you have to interpret in the measure theoretic sense. So in the end, if you combine all these results, then you see that you can go, at least for the classical obstacle problem, from almost nothing to real analytic, and that's you know, the achievement. This is the crowning achievement of the theory of the regularity of the free boundaries. For the lower dimensional obstacle problem, I should say right away that well, there is a person in this room that is that has some news concerning this part here. This part here for the thin obstacle problem is a fundamentally open problem, and but I think that when Ui is working with Herbert Koch, and Herbert gave a lecture here about a couple of months ago. So they have some very interesting progress in this direction. So for the lower dimensional obstacle problem, we have the following mathematical formulation. So think of a domain D, and think of a n-1 dimensional submanifold that divides D into two parts, D plus and D minus. I will mostly concentrate on the situation in which this manifold here is a flat manifold. So the picture that you have to keep in mind. So this may be the general situation, but I will really look at this one. So for me, this will be xn equals 0. So think of this as the xn axis. So this is going to be my thin manifold. I'm going to denote it with D1 prime. This is D1 plus. This is D1 minus. And my domain D will be the unit pole. Okay? So this situation is, you know, hard enough already. That it presents all the challenges of the problem. So again, we want to minimize, I'm taking as source term 0, and I want to minimize the energy over the closed convex sets. Again, there is a unique solution to this problem. This was proved by Fichera in 1963. So the problem was posed by Signorini in 1959 during a course that he taught at the Istituto Nazionale d'Alta Matematica in Rome. And he called it a problem with ambiguous boundary conditions. You will see it in a moment. because there is a set of two alternative boundary conditions that the solution must satisfy at any given contact point. And a priori, you don't know which one is satisfied. You just know a condition, a nonlinear condition between the two. So as I said, Fichera, who was a student in that course, was able to solve this problem, prove existence and uniqueness of a variational solution to the Signorini problem. Anyhow, so that's a picture for the Signorini problem. So we have manifold M defined in the domain D, and we have an obstacle, okay, defined on the manifold M. And so the solution has to lay over the obstacle, like in this picture here. So this is a natural problem that arises in elasticity. Okay. So again, we look at the coincidence set. The set, now we are looking at points in the manifold where U is equal to coincides with the obstacle. And the boundary in the relative topology of M of this set is called the free boundary. So as I said, there are various situations in which this thin obstacle problem arises. And I've described here a few of them, but I will give you some pictures now about this particular situation, the problem of osmosis. So because that's a typical problem in which you get a parabolic Signorini problem. So suppose you consider a semi-permeable membrane. Okay, so semi-permeable membranes are membranes in which only a certain type of molecules the membrane is permeable only to a certain type of molecules, which are the solvents, and blocks other molecules, which are the solutes. So due to chemical imbalance, the solvent flows through the membrane from the region of smaller concentration of the solute to the region of higher concentration. This is called osmotic pressure. And the flow, of course, occurs only in one direction and continues until a sufficient pressure builds on the other side of the membrane to compensate for osmotic pressure. At that point, the flow shuts. So that's this phenomenon here is described in this beautiful classical book of Duvaux and Lyons. If you look at the chapter on semi-permeable membranes, you will see this problem described mathematically in a beautiful way. So, so let me say a few more things. So we have an open set omega and a portion of the boundary which is going to model the semi-permeable part of the boundary, the thin manifold. Okay, so we have phi, which is going to be the osmotic pressure, is the obstacle. The obstacle is going to be defined on M Cartesian 0t. So we have time involved here that also goes, outside of the board here in this direction. So, and then the pressure of the chemical solution is the solution satisfies the heat equation. Okay, so on M Cartesian 0t, so we have the following boundary conditions, which are the condition of finite permeability. So when U is above the obstacle, then there is no flow. Okay? And when U is less than or equal than the obstacle, then you have this condition here for a certain parameter lambda. Now, as you let this parameter go to infinity, so here is the picture. So you have MT here, you have no flow on this side, you have flow on this side. So when you let lambda go to infinity, you obtain the following conditions on MT. These are called the infinite permeability. So U bigger than or equal than phi, we already talked about this. So the U d nu is bigger than or equal than 0, and this is what Signorini called the ambiguous boundary conditions. Okay? So you see you have the product of these two quantities, and you know that is 0, but you don't know at which point a priori each one of them is true. So this is the picture, and Since we know that u should stay above phi on MT, then phi is known as the thin obstacle. The problem is known as the parabolic Signorini problem. I mean, this is not exactly the problem that was posed by Signorini, but it's modeled exactly on the Signorini problem. So then there is a variational formulation of this problem. You have this variational class. I will not describe this. This W12 of omega t. Omega t is omega cross 0t from now on. So then this is standard Sobolev spaces, parabolic Sobolev spaces. So anyhow, so if you impose reasonable initial conditions in this problem, and then you get the existence of a unique solution. And the solution, and this is of course, a typical model of a free boundary problem. So you have the coincidence set that in this picture is described by this lambda, and then you have the boundary of the coincidence set, which is the free boundary. Okay, so one is interested in the structure and the geometric properties and the regularity of the free boundaries. But before you do that, there is a fundamental step that you need to face, and it's the optimal regularity of the solution. Without the optimal regularity of the solution, you don't go anywhere in the study of the free boundary. Okay? So let me talk a little bit with let me recall very quickly what is known about the classical Signorini problem. So as I said before, I will take B1 to be the unit ball. B1 plus will be, so the thin manifold will be this, the intersection of the unit ball with xn equal to 0. Okay, and the obstacle will be C11 of B1 prime. You can think of this function by introducing a fake variable as a function which is C11 in the whole ball. Okay, and then we have the boundary datum. All right, so here are the properties of the solution U, and again, here there are the Signorini conditions, as you see. So this has to be satisfied on the thin manifold B1 prime. And then there is also this condition, which is, the validity of the Signorini conditions in the weak sense. All right, so this is all you can work with. So let me tell you a little bit about the history of the problem. Caffarelli already in 1979 proved that when M is a flat manifold, so it's a hyperplane, the obstacle is C2 alpha for some alpha less than 1/2, and the coefficients, he actually looked at the general divergence form operators. The coefficients are C11, then the solution is C1 alpha up to the thin manifold. Be careful, the gradient is not continuous across the thin manifold, okay? It's only, the gradient is continuous from both sides, but it has a discontinuity across the thin manifold. So Arkhipova and Uraltseva in 85-87 generalized this result to, to variable elliptic and parabolic operators in divergence form. So they proved, they extended Caffarelli's result to this situation when the coefficients are in W1P. So for some P bigger than N, obviously this case includes also the case in which you have Helder continuous coefficient by Morray's theorem, or here you get Lipschitz coefficients. Anyhow, so what about optimal regularity of the solution? Well, when the manifold is flat, the best that one can hope for the optimal regularity is this one, C1 half, up to the thin manifold. The reason for this is that there exists, it's looming in the dark, this global solution to the obstacle problem, okay? So if you take a real part of x1 plus I, absolute value of xn to the 3/2, then you see that this function is precisely of this class, okay? And this is a global solution to obstacle problem with thin manifold xn equal to 0 and obstacle 0. And you see that along this, if you think of this as defined in the plane, for instance, this would be the place where you split this function here. Okay, so it would be the negative x1 axis. Along the negative x1 axis, the gradient has a discontinuity. So, So in 2004, in the case of the Laplacian, Athanasopoulos and Caffarelli, as I said before, they established this optimal regularity. So they proved that for any n bigger than or equal than 2, when the manifold is flat and the obstacle is 0, you have the C1 1/2 log, up to the thin manifold. There is a paper by Richards on 1978, which was his PhD dissertation, never appeared in print, but you can learn a lot of beautiful things about two-dimensional solutions of the Signorini problem. So in this dissertation, which is available, you can get it online from the University of British Columbia. So when n is equal to 2, Richardson had already proved this result. But his methods are based on complex analysis and do not extend to higher dimension. So this result of Athanasopoulos and Caffarelli really was a major breakthrough at that time. Okay, so let me give you a little bit of historical background. People who have worked on the classical obstacle problem know that oh man.
No, it's maybe the computer. No.
Oh.
Your own computer.
Thank you.
No.
Yeah, it takes some time. I mean, it has not at lunch. So the computer.
So you said to some 20 minutes or something.
Yes. Yes. So if you have looked at the classical obstacle problem, I mean, then you know that these objects here, since in the classical obstacle problem there is only one type of homogeneity, which is quadratic. So this quadratic rescaling here is, is the thing that one looks at. So one considers these rescalings, and following an idea of De Giorgi in the study of regularity of minimal surfaces, you blow up this function nu at a given point, for instance the origin, and you study the limit configurations, okay, of this function, and that this limit configuration gives you information on the free boundary, and also about the optimal regularity of the solution. So what happened in 2007 is that Athanasopoulos, Caffarelli, and Salsa introduced a completely new family of rescalings, which is this one. So now notice that the factor r squared has been replaced by this thing that depends on the L2 norm of the solution on spheres. Okay, so it looks very weird that you should rescale in this way, but let me tell you that this is a beautiful idea and works in a fantastic way. If you combine it, of course, they didn't come up with this idea just out of the blue. They didn't pull it, from the hat. What they had in mind is a fundamental result of Almgren, which goes back to 1979, which says that you have monotonicity of a certain quantity, which Almgren called the frequency. So let me talk a little bit about the monotonicity of the frequency. So what Almgren observed in 1979, he actually proved this result for multiple valued harmonic functions because he wanted to use it in his study of the regularity of minimal surfaces, that is, suppose you take a standard harmonic function in a ball and then you look at this quantity here, okay? Then this quantity, which he called the frequency for the reason that I will tell you in a moment, is monotonically increasing in 0, 1. Now notice the object that is down here. So the object that is down here is the same object that appears in Athanasopoulos, Caffarelli, and Salsa rescalings. Okay? So this is a renormalization of the L2 norm of U over a sphere of radius r, which in geometry they call the height function. So this H stands for height function, D for Dirichlet integral. Okay? And it's a very nice exercise to prove this result of Almgren. It's a beautiful exercise. So this is a very deep theorem because it gives you information on the order of 0 that the harmonic function is allowed at one point before it has to become identical equal to 0. And the order of 0 depends only on the L2 norm of the function on a ball of fixed size. Okay. So in 2007, Atanassopoulos, Caffarelli, and Salsa proved that this result of Almgren can be extended to a solution of the Signorini problem. Okay, so they made this observation that that this monotonicity of the frequency continues to be valid for a solution of the Signorini problem, and moreover, which was the reason for which Almgren called it frequency, this function here is constantly equal to kappa if and only if U is homogeneous of degree kappa in B1. So you see, if you take a harmonic function which is homogeneous of degree kappa, then you have a fundamental harmonic function, one of the solid harmonics, and kappa is the frequency of the solid harmonic, and that's why Almgren called this function frequency, because it is constant exactly on the fundamental harmonic functions. All right, so the proof of this result of Atanassopoulos, Caffarelli, and Salsa imitates the proof of Almgren, except that at some point you have to use the Signorini condition. You have to integrate by parts in a clever way and use the Signorini conditions. But everything works out nicely. So let me show you why this monotonicity of the frequency plays a crucial role in the analysis of the blow-ups. By blow-ups now I mean the one that were introduced by Atanassopoulos, Caffarelli, and Salsa. First of all, it implies that the blow-ups exist, so that when you go past to the limit, the blow-ups, the rescaled, they actually go to a limiting function, which is again a solution of the Signorini problem. It's going to be a global solution to the Signorini problem. So the observation is the following one. First of all, when you look at the frequency, you recognize that it's invariant under rescalings. So if you take the frequency of a function u at level r, then that's the same as the frequency of the rescaled function ur at level 1, where by rescaled, I mean this rescaled function, okay? Notice that this rescaled function has L2 norm on a sphere of radius 1, which is 1, by definition. You make a change of variable here, you bring everything to sphere 1, you get 1. So that's a trivial but important observation in a moment, as you will see. So we use this property here, this scale invariance, and then we use this trivial observation, okay, which I just made. And then we proceed, and we look at the energy of the rescaled function on a ball of fixed radius, 1. So this is equal to this divided by this, because as I just told you, this thing is 1. So, but this now, on a ball of radius 1, is the frequency of ur, which is by scale invariance equal to the frequency of u on the ball of radius r. And by monotonicity, this is less than or equal than the frequency of u on the ball of radius 1. So this tells us something very important, that these rescaled functions are equibounded, have equibounded energy. So if you combine these things with the C1 alpha estimates of Caffarelli, 1979, okay, C1 alpha estimates are crucial. We don't know what the good alpha is, but it's a fundamental step in the process. So if we combine this observation here with C1 alpha estimate, we end up showing that there exists, by a standard diagonal process, there exists a non-zero function. Why non-zero? Because remember that this function u0 is going to converge in L2 norm on the boundary of B1. So these URJs converge to u0, and the URJs have norm 1. L2 norm 1. So u0 cannot be 0. Okay? That's important, very important. So there exists a non-zero function u0 in W12 called the blow-up, such that for some subsequence we have this convergence. Okay, now you want to make sure that, when you pass to the limit along different sequences, you don't get different functions, and you can prove all these things once again using the monotonicity. But the first thing that, this little proposition here helps you in identifying the blow-ups. So if you have a solution to the Signorini problem in B1 and denote by U0 any blow-up of U as described above, then U0 is a global solution of the Signorini problem, and it is a homogeneous function of degree kappa, where kappa is the limit at 0 of the frequency. This limit exists because the frequency is monotonically increasing. Okay? And in fact, as you will see, this value kappa will be, a constant. It will be coming back over and over. The value of the frequency at 0 will be coming back over and over in the study of the Signorini problem. Okay. So this result was proved by Sylvester and Caffarelli, Salsa, and Sylvester. So suppose you have a solution to the Signorini problem in B1, assume that 0 is a free boundary point, then the frequency has to be bigger than or equal than 3 Hz. So you can't have frequency lower than 3 Hz. Moreover, either you have it at 3 Hz precisely, or it has to be bigger than or equal than 2. So there is a gap. Okay?
So, sorry, is there are there homogeneous global solutions now?
Yeah, I will describe that in a moment. Okay. So, so now let me go back to the parabolic Signorini problem, okay? So again, I will focus on the case of a thin manifold M which is flat. And this is the main result that we prove with Donatella, Arshak, and Tunto. So suppose that Q is a solution of the parabolic Signorini problem with flat M and the obstacle in a suitable, natural class. With phi 0 is the initial datum and G is the boundary datum, is the lateral datum. Then the gradient of the solution is in the parabolic class C1/2, 1/4. So in other words, the spatial gradient is Helder continuous with exponent 1/2 in space and Helder continuous with exponent 1/4 in time. And we have this a priori estimated, this is a local result, of course, and this result is sharp, of course, because if you take the global solution, real part of x1 plus I absolute value of xn to the 3/2, that is a solution to a parabolic Signorini problem with 0 obstacle, okay? So.
I'm sorry, can you cook up global solution, a explicit solution having the optimal regularity at the time sections as well?
Yeah.
Yeah.
Yeah. I will, hopefully I will show you some.
Okay.
Okay. So let's see. Let me write G. G is the Gauss-Weierstrass kernel, so the classical heat kernel. So I will go back now to a monotonicity formula that was proved by Poon. Poon, he was a student of Fang Guolin. He established a parabolic analog of Almgren's monotonicity of the frequency. So this is the result of Poon. So suppose you take a solution of the heat equation, caloric function, in the strip Rn clos minus R2, 0. So this is the time variable here, the time interval. Then this quantity here, so you're integrating on time slices. At time t equal minus r squared, you're integrating only in space. Okay, so this quantity here as a function of r is monotonically increasing. So here you have to think of this as a global version of the energy. So you opened up the ball somehow and multiply for the Gaussian measure. Okay, remember I'm multiplying here, this is a one parameter family of Gaussian measures. Okay, and this is the equivalent of the height function. Okay, so and moreover Poon observed that this quantity is equal to kappa if and only if U is parabolically homogeneous of degree kappa. So which means this. When we deal with the heat equation, we have these non-isotropic dilations, okay, which are the natural dilations of the heat equation. All right, so So now let's go to the parabolic Signorini problem. So I'm taking as Q1 plus, so this is B1 plus, this is B1 plus, okay, cross minus 1, 0. M is B1 prime, so this is my M here. And phi is the obstacle, which is going to be defined on B1 prime cross a time interval, okay? So I'm going to start with a solution. Ooh, there is, we want to extend V. So lemma U is equal to V, okay? Except that V will become a different thing later on. So I apologize. So this U here should be the V. I'm sorry, this V should be U. I'm getting confused myself. So, so the first thing that we need to do, let's go back for a second to Poon's result. Notice, let U be a caloric function in the strip. So this is a global statement, okay? However, when we work with the Signorini problem, we have a local solution. So we somehow have to cut it off so that we extend it to solution to a global equation. However, there is a problem, of course. If I take a cutoff function in space, function eta, usual bump function, and I call V U minus the obstacle multiply. Notice that I'm subtracting the obstacle so that I reduce myself to the case of zero obstacle, okay? And multiplied by the cutoff function, then this function V solves the Signorini problem in the half strip Rn plus. Here, Rn plus is the half space, okay? Cross minus 1, 0. Again, minus 1, 0 is the time interval with a non-zero right-hand side. So if I take Laplacian V minus dtV, I get this mess here. Notice that even if the obstacle is 0, I still get a non-zero right-hand side, because even if the obstacle is 0, so this guy is not here, this guy is not here, but I would get U times Laplacian eta, and I would get 2 gradient U gradient eta. So we get some junk that we have to deal with. Unfortunately, dealing with this junk is not so easy. Unfortunately. Okay, so I've already made this observation. So let me now go to the analog of Poon's truncated objects here. So first of all, we defined these quantities here. This is the analog of Poon's function, and this is the, Poon's height function. This is the analog of Poon's energy function. The Poon's frequency would be given by the quotient of these two quantities here. Okay? However, there is a little problem. If you start working with these quantities here, your solution U does not have enough regularity to carry out all the calculations. There is really some serious obstruction. So what we did, we took some Steklov averages. We looked at, there is a classical device when you work with the heat equation, in fact, to make up for the fact that you don't have, for instance, you don't have good information on time derivatives of the solution. So you take Steklov averages of the solution, and that's what we did. You have to keep in mind that this may not be so apparent from the formula, but when you look at the frequency function, every frequency function is very well behaved and very stable under averaging processes. You take any sort of averages of frequency function, and they're still monotone increasing. Okay? So that's what we did. Although, I mean, it took us a while before understanding this aspect here. So we took averages of the quantity that are defined here. So these are really Steklov averages, you see. Okay? So, and we work with these things here. And in the end, this is the main result that we prove. This is, V is a solution, a normalized solution to the Signorini problem in this half strip S1 plus. With the right-hand side, so V satisfies the equation H of V equals F. So this F here as a superscript will denote, solution of the Signorini problem with the right-hand side. And we had to incorporate the right-hand side because we have it in our problem. So then, for any delta bigger than 0, there exists a universal constant c bigger than 0, depending also on the L-infinity bound on f. So here f is an a priori L-infinity function, such that this quantity here, so this is a truncation of the height function here. So is equal plus this object here. This object is innocent, as I will, as you can see, when r goes to 0, this quantity trivially has a limit. What is important is that this is going to have a limit, okay? So this is monotony increasing. Why do we need to truncate? Important fact, okay? This was already recognized by Caffarelli, Salsa, and Sylvester in 2008. When they looked at the case of non-zero obstacle and they proved the optimal regularity for non-zero obstacle, in the case of regular free boundary point, the natural device, when you work with an obstacle problem, is to subtract the obstacle. If you subtract the obstacle, your solution U no longer satisfies the equation Laplacian U equals 0 of the coincident set, but satisfies the equation Laplacian U equals F. Now, if you're trying to establish monotonicity of something in the region where Laplacian U is equal to F, it's a big mess. It does not work. Because, you know, think about think about a classical solution of this equation here. You can put on the right hand side even a smooth function, which has a 0 of infinite order at a point. Okay? You start with a function which has a 0 of infinite order, compute the Laplacian, and you get this function f here, which is very nice and smooth. Compute the frequency of this function, and you see that the frequency is not monotonically increasing. Okay? So there is a reason for it. Is that when you look at solution of Laplacian U equals f, hells break loose. I mean, you don't have any control of the order of 0, whereas the monotonicity of the pure frequency gives you a control of the order of 0. So what Caffarelli, Athanasopoulos, oh, by the way, suppose that we're dealing with Laplacian U equals f, then we don't need to take this truncation. I don't need to take the maximum between the height function and a power. It's enough to work with the logarithm of this. And if I work with the logarithm of this, then I'm back to Almgren's frequency formula because of this fact here. If you compute the derivative of the height function, that's a simple calculation, you get this object here. Okay? So then if you divide by h of r, which is the derivative, the logarithmic derivative of h. So on this side here, after I divide by h of r, and here I divide by h of r, I multiply by r, 1 over r, you see what I get? I get n minus 1 over r plus twice the frequency divided by r. That is the frequency divided by r. So when I'm working with Laplacian U equals to f, for which this formula holds, if I multiply by r here, r times the logarithmic derivative of h is equal to a constant plus the Almgren's frequency. So that quantity, which is what you need, whose monotonicity is what you need to know to prove optimal regularity, the monotonicity of that function is equivalent to the monotonicity of the frequency. However, when you have Laplacian U equals f, this breaks down completely. And that's why Athanasopoulos, Caffarelli, and Salsa looked at the truncation of the height. Because if you truncate the height with an appropriate power, that, you know, it's the critical growth. So then, that depends, of course, on the right-hand side that you put in the equation Laplacian U equals f, then that quantity still has a chance to be monotonically increasing. And so this is what we prove. We prove that this result, and then with this result here, we can study the blow-ups and obtain optimal regularity. Let's see. During how much time? Go ahead.
15 minutes.
15 minutes? You're scaring the audience.
May I ask you a question?
Sure.
So in this monotonicity formula, the F more or less depends on the C11 norm and the DT norm of
Yes, of the
phi.
obstacle.
And there's, is there any way you can go below that on phi? Like C1 alpha and C alpha in time or something?
No.
No, that's
Yeah. I mean, with this method, you're down. Essentially, C11 is the best that you can deal with. Yeah. So we consider this so-called parabolic rescalings. You see, they are modeled on the elliptic rescalings that I told you before of Atanasopoulos, Caffarelli, and Salsa. We are dividing so we are taking the parabolic rescaling of U and dividing by this height function to the 1/2, okay? So, and then you have to renormalize also the right-hand side, and then you see that this rescalings UR, if the value of the frequency at 0 is less than 4 minus delta, notice that the 4 minus delta is the critical threshold that appears here, okay? So if the limit, so this function has a limit at 0, right? It's monotonically increasing. So you look at the limit at 0. If the limit is strictly less than 4 minus delta, then you can prove that the rescaled family UR converges in a suitable sense in the half strip Rn plus cross minus infinity 0 to a parabolically homogeneous function U0, which is a global solution of the Signorini problem. So now we have a global solution of the Signorini problem. Here there are the Signorini conditions, okay? So parabolic homogeneity of U0 is kappa, which is 1/2 times the limit at 0 of this rescale. Again, there is a typo here. There should be U here. The limit at 0 of this rescaled, of this truncated frequency. So kappa has to be less than 2 minus delta because phi is less than 4 minus 2 delta, you see. And so this is strictly less than 2. Moreover, we already know C1 alpha regularity by Arkhipova and Uraltseva, okay? And therefore kappa has to be bigger than or equal to 1 plus alpha, okay, which is strictly bigger than 1. So this already tells us that kappa has to be between 1 and 2. Okay. Thus, I'm getting to the analog of the gap result of Caffarelli, Salsa, and Silvestre. So let U0 be a parabolically homogeneous solution of the parabolic Signorini problem with homogeneity kappa. Then necessarily kappa has to be 3/2, and the U0, after a possible rotation of the coordinates, has to be the global solution, the time-independent global solution of the Signorini problem. Okay? This result is not so easy to prove. So the proof, our proof, is based on the deep monotonicity formula of Luis Caffarelli for the classical heat equation, in which he extended the classical result in which he extended the Alta Caffarelli-Friedman formula. Okay, and then that reduces the problem to 2 dimensions, and then in 2 dimensions you have to analyze the principal eigenvalues of the Ornstein-Uhlenbeck operator in R2 for the split planes which are written there. So, so that's a classification of our global solution to the Signorini problem with a given homogeneity kappa between 1 and 2. So now let's go back to the proof of optimal regularity. So from the lemma, we know that the homogeneity at 0 has to be bigger than or equal than 3. So if it is less than 4 minus 2 delta, that's what I showed you before. And therefore, we always have this thing here. So that implies that the height function has to grows at most like r cube. But now if you have to work a little bit with, we have to prove some a priori estimating Gaussian spaces, so that to replace elliptic theory. So then we show that the supremum of u on q plus r over 2 is controlled by constant times r to the 3 halves. And that at any free boundary point. So, and that if you again use interior parabolic estimates, you prove the optimal regularity, okay? So that's the very sketchy proof. It's probably 30 pages of computations, but that's like. So, regularity of the free boundary. So let me quickly tell you something about the regularity of the free boundary. So again, similarly to the elliptic case, free boundary points are classified according to their type of homogeneity. So we call regular those free boundary points which have minimal homogeneity, kappa equal to 3 halves. Remember, the minimal homogeneity is 3 halves, we know this. So, and we call singular those free boundary points at which the coincidence set as vanishing density in the thin space with respect to the Hausdorff and Hn measure. So that's a definition of a singular free boundary point. Remember that this object here denotes the thin manifold, the thin ball Cartesian with a time interval of length r squared. So at points where this happens, then we call those singular free boundary point. Keep in mind that the free boundary might be made exclusively of singular free boundary points. So you can't stay away from analyzing these points, because it's not true that you only get that generically you get regular free boundary points. Generically, you might get exclusively singular free boundary points.
Is it not true or not proved that you have?
No, you can show solutions to the Signorini problem for which the free boundary is made up exclusively of singular free boundary points. I think that there is a slide later on. Okay. So the regular set is a smooth space-like hypersurface in the thin manifold. That's the main result that I want to prove. First important step in this program is to show the Lipschitz regularity of the regular set. So right now I'm denoting with this notation the regular set, so the set of all regular free boundary points. So again, you take a normalized solution to the parabolic Signorini problem with phi in a suitable parabolic Helder class HLL over 2, notation of Nina, Solonikov and Ladisenskaya. So 0 is a free boundary point, is a regular free boundary point, so the homogeneity at this point is 3 halves. Then there exists a delta and a G, which is in a suitable parabolic Helder class, such that after Helder means in this variable here, which is the t variable, in the space variable the function is Lipschitz continuous, such that after possibly a rotation of the coordinates, one has that gamma v intersected with the q delta prime is described by xn minus 1 equal g of x double prime. So you understand this notation, because remember, I'm looking now at, so I have, I'm in the thin manifold. In the thin manifold, xn is equal to 0, and I have xn minus 1 and the other variable. This is a variable in Rn minus 2, okay? So, the set where V is above the obstacle is described by these inequalities here, so it's the region under the graph. And maybe okay, so I have to talk about Wenuri again. So in order to establish the C1 alpha regularity of the free boundary, of the regular part of the free boundary, we follow an idea of Athanasopoulos and Caffarelli. So back in the 80s, Athanasopoulos and Caffarelli made this beautiful observation that if you take the boundary Harnack principle and you apply it to a directional derivative of a solution, then you get you know, the boundary Harnack principle. Essentially, maybe I should I don't know if I'm trying to tell you what it is, but in the elliptic case, it tells you this. If you have two non-negative harmonic functions, so u equal to b equals 0 here, let's say, and they are two non-negative harmonic functions in here, then everywhere in here, you know, same scale, so suppose this is 4r, this is r, and this is a non-tangential point AR, then ux over bx is goes like u at AR divided by v at AR everywhere in this region here. So even when you get close to the boundary. So this tells you in particular that all non-negative harmonic functions which go to 0 at a portion of a boundary point, they must go to 0 at the same rate. Okay? That's a fundamental theorem which is called the boundary Harnack principle, and it's equivalent to the doubling condition for harmonic measure. So this was proved this theorem was proved by Caffarelli, Fabes, Mortal, and Salsa for divergence form elliptic equations in Lipschitz domain, and simultaneously by Jerison and Koenig for the Laplacian for non-tangentially accessible domains. And that's where we get with the theory of the free boundaries. All right, so what Athanasopoulos and Caffarelli observed is that if you apply that result to, you know, they first established the non-negativity of derivative, of directional derivative solution to the free boundary problem. And then if you apply that result to this non-negativity, to this, you take as one of the two functions, you don't need to have both non-negative, you only need the function in the denominator to be non-negative when you look at the proof. You know, the directional derivative, you end up proving that directional derivatives are C alpha. So you end up proving C1 alpha regularity for the solution of, for the free boundary at regular free boundary point. So Arshak, Petrosyan, and Wenui, they generalized this result to the parabolic setting. So this, I mean, you have to work in the thin manifold, and this is non-trivial at all. I mean, so this is a beautiful result of Arshak and Wenui, and we use this result. We combine this result with, you know, to prove the Holder regularity of the spatial gradient of the function g in the previous theorem. So at this point, what we know, so if we go back for a second to the previous theorem, we know that a regular free boundary point, this function g, which describes the free boundary now, is C1 alpha in the thin manifold. What is missing is the Kinderlehrer and Nirenberg, going from C1 alpha to C infinity. This is a big open problem at this moment.
So you can see one alpha in the spatial variables and in the time.
The function g is Lipschitz Helder, and the function g here, oops, I'm sorry, is Helder alpha over 2. In the time.
So the time, what do you know about the time?
We don't know anything about the time. There is no time here. Right. Okay? So we don't know anything about the time. All right, so here is the picture. Okay? Well, I don't want to abuse everybody's patience. I think I'll stop here. I just want to say that subsequently, we analyze the singular free boundary points, and we developed, you know, the analog to what Arshak and I have done in the elliptic case. But in order to do that, we had to prove one parameter family of monotonicity formulas, a Weiss type monotonicity formula, which is, so this this formula here, remarkably, that's what Ashok and I discovered in our elliptic paper, is that these one parameter type formulas are in fact deeply connected to Amgren's monotonicity formula, in the sense that Amgren implies these formulas and these formulas imply Amgren. The difference with the original formula of George Weiss is that in the classical obstacle problem, you have one only homogeneity, 2. And you don't see this. So, but if you introduce a one parameter family, so if you introduce a homogeneity parameter kappa here, and you look at this functional which generalizes George's functional has a 2 here. Okay? So if you introduce a one parameter family of George's functional, this is in fact equivalent to Amgren's monotonicity formula. So you can get one from the other. I mean, it's not totally trivial, but trust me. So, and so we prove the monotonicity of this functional in this sense. Okay, so this plus this is monotonically non-decreasing. This constant C and this sigma here depend on the right-hand side, F, that you have in the equation. So, and then we showed also a monotype monotonicity formula. So in the classical obstacle problem, Monod, with this monotonicity formula, in which he has only one homogeneity, 2, was able to attack the regularity, he was able to prove the uniqueness of the blow-ups at singular free boundary points, using a monotonicity formula like this, in which kappa was equal to 2. So Arshak and I recognized that once you have this one parameter family of Weiss monotonicity formula, then you can prove a one parameter family of monotype monotonicity formula, and this work well for the obstacle problem, because in the thin obstacle problem, you have infinitely many possible homogeneity. For instance, at singular points, you always have, you can prove this homogeneity 2m, so even homogeneity. So there are these two formulas in which, with this monotype monotonicity formula, we're able to prove uniqueness of the blow-ups, and then you put up the standard machinery that made us work for a while, and then you get regularity of the free boundary at singular free boundary points. So this is this is an example in which you have only singular part in the free boundary. So this is an example in which you have only singular free boundary. And this is the structure theorem that we have for the singular set. So thank you very much for your time.
Questions? Remarks?
So the Signorini, one can look at it as a usual obstacle problem with force term as a measure.
Yeah,
Hausdorff measure.
exactly.
So is there results that this force term is like a good function and converse to this measure, and the solutions converse to it?
I don't know. That's an interesting question. No, I don't know. I don't think that this is so simple, though. It's an interesting question.
Yeah, so I have a question. I don't remember, but in the elliptic case, I remember that you're not really able to distinguish whether you have regular points or singular points or blow up or order degree 2k. Do you still have this? Like, there's a part of the singular
In the
part
elliptic,
that you don't really know.
oh yeah, in dimension 3, because so in dimension 2 you know everything.
Right.
Maybe I should have said this, but in dimension 2 you can sit down and work out an exercise and classify all solutions to the Signorini problem, and you see that the homogeneities that you get are either 2m or 2m minus 1/2. These are all the possible homogeneity that you can get for the Signorini problem, n equals 2. Very important. Okay? So, m equal 1, you get m equal 1, you get 3/2 regular free boundary point. Singular free boundary point, you can prove that if the singular free boundary points must have homogeneity to M, and then you have this other type of homogeneities, 2M minus 1/2 with M bigger than or equal to 2 in the plane. For n bigger than or equal than 3, it's an open problem whether these guys can occur or not. We don't know.
But for the singular set, do you do the analysis for this 2m minus 1/2?
No,
Two.
singular
You can
set.
only do it for 2. Oh, yeah,
No. Singular set, there is a theorem that says that if you have a singular free boundary point, then the homogeneity must be 2m. So when you take the blow-ups, they only have homogeneity 2m. You can't have non-even homogeneity for singular free boundary points. So this exhausts this singular free boundary point in any dimension. But what is not known in dimension bigger than or equal than 3 is whether we can have this type. What happens at free boundary points at which the homogeneity is 2m minus 1/2 with m bigger than or equal than 2. That's nobody knows. Okay.
Now there are a lot problems, physical problem for systems, elasticity, the similar stuff.
Well,
some
John Anderson has recently done some beautiful work on the Lamé system. General systems of elasticity, I don't know.
Yeah,
Okay,
I see.
but John has a beautiful approach that avoids completely the use of monotonicity formulas, because for systems,
Yeah.
yeah.
I see. Also
And
maximum principle.
yeah,
right?
yeah.
All right.
Yeah, and you said that the high regularity of the free boundary is an open question. And is that true both for the elliptical parabolic Signorini problem?
For the elliptic, you have to talk to the person in the room here. So, what is the status for the elliptic problem?
I think so far it seems one can get the analyticity.
So,
If the obstacle is zero obstacle.
okay.
For the
So Wenhui and Herbert Koch have this beautiful result in which essentially they can get from, if you start from C1, I guess,
yeah, C1 alpha.
C1 alpha, you get, so they have the analog of the Kinderlehrer-Nirenberg theorem. And I believe that the remarkable aspect of this thing is that subelliptic equation entered the picture. In other words, when you do this autograph transformation or partial autograph, I mean, when we should talk, because you end up with these nonlinear equations which involve these vector fields, and so they had to develop the regularity theory for these equations.
Thank you.
But for the parabolic, I think that we knew probably tomorrow morning will come up with it. So I think the parabolic is open still. Yeah.
Some other questions? But if not, let's thank Nicola again. There is a pizza and beer which is waiting for us.
I think this would be nice.
Well,